See? Okay.
Stage is yours, not yet.
Not yet.
Now it's yours.
Now it's mine. Okay, so thank you everyone for coming. Now here I'm going to present the idea of a paper that we published on Archive more or less 2 months ago. And basically the idea is, well, as the title says, addressing homonuclear and heteronuclear J-couplings within a given molecule. Now we called this protocol J-insect, and I will explain, well, what's J-coupling and why it's interesting to detect it, altogether with all the issues or the benefits that we have. Okay, so first I'll begin with an introduction, because this work is, well, everything more or less that we do is very related to nuclear magnetic resonance. So I'll first introduce the basic idea and the main issues that this methodology has. And once I've done so, I'll explain why using MB centers or point-like defects are useful to surpass, to reduce, or to cancel those issues coming from conventional NMR. Once I've done that, I will introduce already some of the intramolecular interactions that are interesting in this case. Mainly, I will talk about chemical shift and J-coupling. There are other interactions that I will not mention, but basically the usual ones are these two. And I will talk a little bit about realistic experimental conditions, because it's the point of our work. Once I've done that, I'll introduce the protocol and talk about its different parts. First, I will talk about how we use pi pulses for two main reasons. And then the detection state, because the pi pulses are used for codification, while then you have to detect something with DMB, so this is also a part of our protocol. Once you know the protocol, I will give a more realistic example of a real molecule, that is the one we actually used in the paper, just as a proof of principle to show that the protocol works, although it can be used for any molecule in principle. And finally, I will talk a little bit about the issue, or the issue of having a limited number of measurements in your protocol. And of course, I will end with an outlook and conclusions. Okay, so first, conventional nuclear magnetic resonance. So this technique, since it was invented more or less in the 1950s, I think it has been very, very useful in a lot of different fields, going from organic chemistry, catalysis, biology, or medicine. You know, I guess, when you go to the hospital and take a magnetic resonance imaging, those pictures that you get of, for example, your arm or something like that, well, the basic idea is also nuclear magnetic resonance. It was very useful, and it's very useful still nowadays, because it's a technique that it's not invasive, meaning that you do not have to do something harmful to your sample to get a signal back and detect the things that you are interested in. Okay, so it's very useful because also it has a lot of resolution, but one of the main issues is that it has quite bad sensitivity. This means that the amplitude of the signal that you're receiving is very small, which in the end means that you are limited to using or to detecting macroscopic samples, because if you reduce the size of the sample, the signal that it will emit will be smaller, so in the end you will not be able to detect anything. And this is due to the fact that the method or the technique uses spin polarization as the source of signal. So you have to polarize as much as you can the spins in your sample to get a big signal. But to do that, you have to work at high magnetic fields, but working at high magnetic fields carries some issues. So in the end, the idea is that the sensitivity is not quite good. This is what I said, you need very intense high magnetic fields, and the issue is that these fields need to be very homogeneous for your signal to be very homogeneous as well, and experimentally it's quite difficult to do so. So this is one of the main issues of this conventional nuclear magnetic resonance. So now the idea is, okay, what if I use quantum sensors, and in this case, NB-based NMR. So here, the schematic setup is you have an ensemble of NB centers, so all of these are NB centers placed below a sample that you want to detect made of many molecules of whatever type. Okay, so this idea, thanks to the proximity of your sensor, which is the NB sample, to your sample, it gives you high sensitivity. So you solve one of the problems of basic or conventional nuclear magnetic resonance thanks to the closeness to the sample. And apart from that, you have very great spatial resolution. You can measure up to single cell volume, so it's very, very good. And also, as a side note maybe, you can work at extreme conditions as high pressures, which usually with conventional NMR have very problems, this type of setups. Okay, sorry. So now, more or less, you know the motivation. Let's go deeper into what we want to do. Okay, so imagine that we have a molecule, okay? For now, for you to understand all the interactions, I am only going to focus on two hydrogens of that molecule, hydrogen 2 and hydrogen, well, 1 and 2, and I will forget about the rest of the molecule. All right, so now what we first have to do is apply a magnetic field along the Z direction. So the Hamiltonian of my molecule for the moment will be the Zeeman interaction of both hydrogens. This is for hydrogen 1 and this is for hydrogen 2. Notice how both terms are equal. Okay, so the first thing happens when you take into consideration that each hydrogen has a different local environment, a different molecular environment. Now this has an effect, and that is that each hydrogen will feel a slightly different magnetic field compared to that you are applying, and that is because of the specific molecular environment that it has. So hydrogen 1 will feel a different magnetic field, a deviation, and hydrogen 2 a different deviation. So we have to take this into account in our Hamiltonian, and we have to add these two terms right here, this for hydrogen 1 and this one for hydrogen 2. Now this type of terms is what we call chemical shift. And as you can see, it's a deviation from the normal or the normal, Larmor frequency that they would have if they were isolated. Okay, so this has an effect to your resonance spectrum or to your Fourier space when you Fourier transform it, because if you didn't have these terms, both resonances will be placed at the correct point, taking into account that you are applying this magnetic field. But these deviations move each peak of each hydrogen distance from the resonance, which in principle you should have. So this can give you information about the local environment of each hydrogen. So this is already very useful, this kind of interaction. Okay, and the other type of interaction that you could have in a molecule is a second order spin-spin interaction, which is basically a dipole-dipole interaction, but carried through the bonds, the electrons placed in the chemical bonds of your molecule. So it's an interaction between hydrogen 2 or hydrogen 1, but it's second order because it's mediated through the electrons that are within the bonds of the molecule. Okay, so this, you can write the term in the Hamiltonian, and it's a term like this. And usually, under certain conditions, you can approximate the term to a ZZ type interaction. Okay? And now, this type of interaction, if you recall the previous chemical shift spectrum, what does this new interaction is it splits the peaks that you have that you had into two peaks of half height. So now we know what the chemical shift do and what the J-coupling, this type of spin-spin interaction is called J-coupling, do. And this also can give you information about the molecule that you have in your sample. And our goal in this work is to detect the value of this coupling constant right here. Okay, so now you know the interactions that you can have. Let's go to a more experimentally realistic case. So this is the Hamiltonian that you have for one molecule, but you have to take into account one thing, and that is that in your sample you have more than one molecule. Actually, you have a lot of molecules. And if you take into account that you will have magnetic field inhomogeneities due to experimental difficulties when you want to create a very homogeneous field, each molecule, yeah.
So maybe forgot to say why it's interesting to measure J.
Okay.
Which is the info that provides?
Well, it provides information about, since chemical shift can give you information about the local environment, and this J can give you information about to what that type of nuclei is coupled to.
So like the connectivity.
Yeah, connectivity. Yeah.
Of the chemical bonds.
To what nuclei, to what, how many nuclei it's coupled to. Yeah, yeah. So as I was saying, each molecule in your sample will feel a slightly different magnetic field, which in the end, since your total Hamiltonian is the sum of the Hamiltonians of individual molecules, you will have a deviation from the perfect case. And that is because this term right here, which we call is the Zeeman effect, depends on the magnetic field. And if each molecule feels a slightly different magnetic field, when you sum over all the molecules, this will not add as we would like to. So yes, you have, yeah.
So you're assuming that the magnetic field can change between molecules, but the
Yeah.
chemical shift and the coupling is preserved.
Yeah, because you assume that every molecule is the same. So in principle, the intramolecular interactions do not change, but the magnetic field changing between molecules is due to spatial inhomogeneities in your magnetic field. So if you have a molecule here and a molecule here, they are the same, so the interactions coming from inside of them are the same. But if your magnetic field is a bit different here and here, this term right here will change from one to another. But this term, which has only information about the molecule itself, does not depend on the magnetic field.
It will change because it's proportional to the magnetic field.
No, but you can take that difference into account here also as well, right?
Okay,
I mean, you can.
Parts per million, it's constant.
Mm-hmm. I mean, depending on your definition, you can do whatever you want, yeah. Okay, so this, having a different magnetic field applied over each molecule, will have an effect. Now recall we had this spectrum right here, for the case that I've shown you. But now, taking this effect into account, effectively what happens is that your signal decoheres much, much faster, which means in the end that your peaks will get much wider. Okay? So this is a problem, the magnetic field inhomogeneities. Okay? Because you lose resolution. Yeah.
And in your total Hamiltonian, are not there interactions between molecules?
No, I'm not taking that into account. No, maybe you could, but I guess, that's a good question. Maybe, I would say that since we are in a liquid, those interactions vanish due to averaging of all the directions. And as well, maybe, this I don't know, but maybe these are much stronger, but I would say that the first thing I said is a better answer.
It's like that question because one of the things that we are forgetting this happens even at the intramolecular level,
Mhm.
which means that also happens much harder to be found among molecules. But in the liquid state, that's the way. Solid is a different story, but for liquid, it's
Yeah. Okay, so the effect of inhomogeneities is that you get wider peaks, which is bad because you get worse resolution when you want to resolve given frequencies. Okay, now the other detrimental effect that you can have in an experiment is that in a noisy environment you will have white noise, and when you measure also you will have shot noise. Okay, so this leads to worse signal-to-noise ratio, which in this field is usually related or called sensitivity, and the spectrum goes from this to something like this, a very noisy spectrum, which in the end means worse noise signal-to-noise ratio. Okay, so basically we have two main detrimental effects. One is due to spatial inhomogeneities in your magnetic field, you get worse resolution, and due to this white noise and shot noise, you got worse sensitivity. This means sensitivity is more or less a signal-to-noise ratio, the relation between the height of the peaks and the height of your average noise in your Fourier transform, something like that. Okay, so now knowing this, notice that there is a trade-off. It seems to be a trade-off. If you want to increase the sensitivity, one way to do that is to increase your magnetic field, because you will get higher polarization, and then you will get a signal with more amplitude, thus you will get more sensitivity. But remember that increasing the magnetic field worsens the spatial inhomogeneity of the magnetic field. So in the end, you get worse resolution. So in the end, you want to increase sensitivity, you will get worse resolution if you do not do something to solve this kind of relation. Now, as a comment, you can also increase sensitivity by increasing the number of measurements in your experiment, but it's much more interesting to increase the magnetic field because the sensitivity increases linearly with the magnetic field, while if you increase the number of measurements, it increases as 1 over square root of the number of measurements, or square root of the number of measurements. Okay, so now that you know the things that you need to know, I'm going to introduce the protocol that we invented, which is called J-insect, and it stands for J-coupling induced nuclear signal with extended coherence times. Okay, so as I said before, the protocol has basically two parts. The first one is the detection stage, which is made of pi pulses. Now, these pi pulses have a twofold function. The first function is, well, remember the molecular Hamiltonian for a single molecule. It had this expression right here. And now let's see what happens when I apply a pi pulse over both spins, both hydrogens. So I would let the system evolve freely for a certain time, apply a pi pulse, and then let it evolve again. When I do so, notice how the effective Hamiltonian after the pi pulse is like this, where some of the signs changed due to the effect of the pi pulse. So effectively, I have that before the pi pulse, I have this first Hamiltonian with all the signs being plus, and after the pi pulse, I have this Hamiltonian with some of the signs minus. Now, the effective propagator will be the sum, or the, will be one and then the other propagator. So in the end, if you do the maths, you get that you only keep the information about the J-coupling. So this is very useful. Why? Because if I apply a pi pulse over the hydrogen 1 and hydrogen 2, I know that in the end the evolution is driven by their interaction, their J-coupling interaction, while the other terms will be cancelled. Now, if I only apply a pi pulse over one of the spins, the same thing happens, but less signs in your Hamiltonian change. So in the end, I do the same maths, and I get that the dynamics will not be driven by their J-coupling interaction. So this is very useful because now here I have a way to target specific J-couplings in my molecule. If I am interested in the J-coupling between nuclei A and nuclei B, I apply a pi pulse, simultaneous pi pulse over A and B. But if I'm not interested, I only apply a pi pulse over one of them, so I know that that interaction will not appear in the dynamics. Okay, so this is the first function of the pi pulses. I have versatility to choose what I want to see. And the other function is the cancellation of magnetic field inhomogeneities. And why is that? Remember that when I apply pi pulse, well, first, remember the Hamiltonian, the molecular Hamiltonian, and this term right here, it was the source of the problems coming from the inhomogeneities. So when apply a pi pulse, remember that the effective Hamiltonian or the effective propagator read like this. So with a pi pulse, I cancel also the effects of this term. So thanks to the pi pulse, I also am able to cancel the effects of the inhomogeneities, which in the end means that I can improve the resolution of my protocol at high magnetic fields. So I can work at high magnetic fields, and I do not have to worry about the problems that come with that. All right. So now I've explained the detection, the encoding stage. Now I'm going to explain a little bit the detection with the EMB. So first, well, to detect in our protocol, we use the ARES protocol, which was designed by Carlos, Jorge, and Ander. It's an heterodyne-like measurement. This means that with these types of measurements, I do not have to worry about the decoherence of my sensor. So the EMB center usually have a decoherence time which is quite low, but with this type of measurements, that is no longer a problem. So this is one good thing about this type of measurements. But the new thing with this protocol that they proposed is that it's a protocol thought to work at high magnetic fields. This means at high magnetic fields, your signal will be oscillating very, very fast. Usually, the EMB center is not able to detect high oscillating frequencies from one threshold frequency, but this protocol allows you to detect those high rapidly oscillating signals. Okay, so with other methods, you would have don't worry about the Hamiltonian. I just want you to know that the EMB would have to detect with other methods signals that oscillate very, very fast, which is quite difficult with the EMB center. But with this method, you, with the EMB, have to detect something that oscillates with a frequency that is set by you. So this is quite interesting. And the information that you want to detect is encoded in the proportionality constant right here. So this is a very good idea. When they proposed this, they were very smart. Okay, so then what you have to do is repeat the encoding process a lot of times, and then in the end you can reconstruct a signal that encodes the information about the J-couplings in this case. Now that you know this is more or less the structure of the protocol. So you have first an encoding stage. So here you let the system evolve freely. It will evolve under J-couplings, chemical shifts, etc., etc. You apply the pi pulses that you are interested so that you want, and then you let the system evolve again for the same amount of time. So recall that after this this process, you will only keep the information about the J-couplings, and you will cancel, in principle, everything else. And then you detect with this heterodyne-like measurement. And then you repeat again and again and again and again, and you reconstruct a signal that encodes the information that you want. All right, so now you know everything, and here I'm going to show you a more realistic example as a proof of principle to show you that this method works. So we chose as for the example this molecule, fluoromethanol, and we chose it because it's a more or less simple molecule, but it has a lot of different elements which allowed us to show the versatility of the protocol. So it has two hydrogens which are the same, meaning that they are equivalent, equivalent. The other hydrogen is chemically inequivalent, sorry. And then we have a carbon nucleus and a fluorine nucleus. And the oxygen, it has no spin, so we don't worry about that. So notice here that there are a lot of different J-couplings. And now I'm going to show you what can we do to target one, the other, or all of them. So first, the full Hamiltonian would be something like this. This is the chemical shift terms. Now, it would have also a homonuclear J-coupling term, which means an interaction between nuclei of the same species, in this case of the hydrogens. And then in the end, it would have an heteronuclear J-coupling terms, which, well, is the rest of interactions that you can have between hydrogen-carbon, hydrogen-fluorine, etc. Okay, so with this, now, for example, if I apply a pi pulse over only hydrogens and carbons, I get that in principle only target the interaction between hydrogen-carbon, hydrogen-hydrogen, and carbon-hydrogen again. So the spectrum that we get is this one right here, and each peak of this spectrum has encoded the information about these J-couplings right here. I'm not going to show you the analytical expressions, but yeah. And then, if you want to detect not only these J-couplings, but all the J-couplings, what you have to do, as I told you, is apply a pi pulse also over the fluorine. And if you do so, you get a much more complicated spectrum, but that is because now you're targeting much, a lot of interactions right here, because you have to add the ones corresponding to the fluorine. But this you can solve analytically, and then you can extract the value of each coupling right here. So yes, very useful. This is an example, but we showed that it actually works. So now, to finish, I would like to talk you to explain to you the number of measurements limitations that, in principle, we have in this protocol, because recall that the structure was this one. If I want to increase the number of measurements, what I have to do is squish the detection stages. This means making this tau times smaller and smaller, right? Because if I squish it, I will be able to put more detection stages within the whole protocol. Okay, now, but there's a problem with that. Remember that the whole Hamiltonian was this one, and especially look at the homonuclear J-coupling, which is a term, a ZZ type term, okay? So this is what we had until now. But if I squeeze it, but there's a condition, there's a condition for this term to be like this, and that condition is this one. So if I want the term to be a ZZ type, tau cannot be smaller than this quantity right here. Now, the reason for that is some rotating wave approximation not being fulfilled, but the thing is that if I reduce tau, there will be a point where this is not true, so this term is no longer of this form, and actually, if I do it, the term is of this form. Okay, so this complicates a lot your signal and thus your spectrum, so you are no longer able to extract that easy your information because you cannot solve analytically your problem. But there's still hope, because you can, well, first let me say that if, for example, you increase the number of measurements by a factor of more or less 10, you get a sensitivity improvement of 3.3, more or less. So this is why it's also interesting to increase the number of measurements. But as I was saying, the spectra become very, very much more complicated. The red one was the easy one, and when I increase the number of measurements, I get this blue one, which is much more weird. Okay, so as I said, there's still hope, because I can do statistical methods. I can use statistical methods to extract the information, and for example, I can use Bayesian analysis, and the basic idea of this method is, well, I obtain a set of data from my experiment, which encodes the unknown frequency that I want to detect. Okay, so for example, I have this kind of oscillatory signal. Now, the data is each point of each signal. Now the next step is I have to simulate various signals with different trial frequencies that I might guess or I might swipe. Okay, so for example, the blue one was the experimental one, and the red one and the orange one correspond to guesses that I did. Okay, and then what I have to do is to compare each trial frequency with, each signal made of the trial frequencies with the real one, and to compare it I use Bayes' theorem, and in principle this theorem will give me like a probability distribution of the value of each trial frequency, and if I do so, I get a probability distribution of what is the real value of my frequency, and notice how it's quite close to the real one. Okay, so we did this with this case, with this complicated case, and we got quite good results. Notice how, well, the vertical line corresponds to the correct value, and these are the probability distributions that we got once we applied this method, so we were quite happy with that. But this method has one issue, and it is that it's computationally very expensive. Well, this means that if I start increasing the number of frequencies that I want to detect in my problem, in the end it becomes impossible to computationally swipe for all of them. And apart from that, I require some knowledge beforehand if I want to apply this method, because I kind of have to know how is the structure of my Hamiltonian before. And you might not know that. But yeah, well, this is like the first step. Then if you want to improve it, I guess you can do better things. So that was it. To conclude, let's recap a little bit what I've said. First, we designed a versatile protocol, versatile in the sense that I can target specific J-couplings in my molecule, and it works at the microscale, so nice. Then it uses an heterodyne-like measurement, so I can work without worrying about the dephasing or the decoherence of my sensor. And it's only affected by the T2 of the sample. This means that I have extended the decoherence of my sample to, I do not want to say the maximum value, possible value, but I have extended a lot the decoherence of my sample by cancelling the effects of the magnetic field inhomogeneities. Okay, and apart from that, I can work at high magnetic fields, which leads me to higher sensitivities. And an outlook for that would be, okay, here we could try to design a more complex protocol to detect hidden J-couplings. I didn't talk about that, but in some molecules you have J-couplings which you are not able to detect, even when applying this kind of protocol, so it would be an extension of this work. And the other one could be, well, design data processing schemes or neural networks to be able to like interpret these complex spectra that I showed you before, and you do not have to use, for example, Bayes' theorem, which is very expensive. And well, cancel further detrimental effects during, for example, your detection stage. So this would be it. Thank you very much for being here, and questions?
I always find it very fascinating that we can address the patterns within algorithms. You know, what's the illusion between this, and are there like spatial inhomogeneities when you do this by process? And would they have an effect on your system?
Okay, so I'm going to answer the first one, and then the second one, could you repeat it? Okay. So the first thing is not that you target a specific nuclei spatially. You send a radiation which touches everything, but you send that radiation on resonance to the resonance frequency of that specific nuclei. So you touch the other one, but since they are of resonance in principle, of course there are second order effects and those things.
Yeah.
But you target specifically with for that nucleus or principal.
Yeah, again, my main question is the second one, which is so I am like homogeneities because when you are, if you send this signal and it's interacting with every molecule, maybe the first molecule is interacting and like observing the same signal as the first one. I mean,
Could you repeat?
I know especially homogeneity.
Yes.
In that signal that you are sending to introduce the bytecode.
So your question is, what does the
How homogeneous is the variable?
how?
Homogeneous is the variable.
Ah, okay. So
Spatially, not in time.
so you mean okay. So if you have also homogeneity if you're in your drivers or something like that. Oh, well, we did not take that into account, but I think, but actually on our simulations, specifically that we did not simulate it, but we actually simulated deviation from your Ravi frequency in your driving, which I would guess it simulates the same effect, although I'm not so sure. But with that simulation, actually I didn't say it, but for the real numerical simulations, we designed 5 pulse structures that are robust against this type of effects of deviation from your Ravi frequency in your driving or your, if you have, for example, a detuning that you are not able to target specifically the resonance frequency that you are aiming to, our simulation used a type of pulses which are called corpus pulses, which in principle take into account or are robust against those type of effects. Or, yeah.
One comment there, which is perhaps physical, is that the pulses are on the radio frequency. Right? That means that the wavelength is super extreme. So that means that essentially there is no deviations to respect, and there are no difference between the radio frequency here and the radio frequency. This is especially separated because the wavelength is very large, right? On the other, much faster than centimeters or
But the magnetic field that is constant.
the magnetic field is not generated in a different manner. Right? Also, one of the things, because they are generated through a solenoid, right? And typically only in the center, right? You keep more or less homogeneity, but we were checking these numbers, right? And the deviations of the magnetic field constant is one part of the yes. Mistake as well. Typically in high precision experiments, typically, these things always affect to the precision of the measurement that we are looking for the same precision. Hertz. Yeah, but this has to be looking into account. Yes.
Well, in this case, you don't know much about the molecule, and you say, okay, I want to study, and you don't target a specific J-coupling because you don't know if there is one. So you just do the thing, you apply a bypass to every single qubit, and you get this weird thing.
This one. The blue one or
The blue one.
okay.
So is there like a relation between the amount of J-couplings you have and how weak the spectrum is in the sense that you need more computation time to extract information?
Well, in this case, there's another thing, and this is the case where we were trying to increase the number of measurements, so the Hamiltonian was not perfect. And this is why it's weird itself. But your question wants to include that, or you don't care if, for example, here, the spectra were much simpler here, but it's still very complicated.
Yeah, this case.
Okay, so yeah, the number of J-couplings that you have, of course, it will complicate the spectrum, but it will complicate it in the sense that you will get much more peaks. But the peaks, each of them will have the same meaning in the sense that the splittings are the same. So if you did not have J-couplings, you would have chemical shifts. And due to having a lot of different J-couplings, those peaks split in a lot of different peaks, but you can track that. But
this doesn't increase the complexity of the Bayesian analysis.
No, by Bayesian analysis you do when you are not able to analytically solve this, in principle. This is solvable analytically. Of course, if you increase more and more the number of J-couplings, it will be harder computationally or physically. But in principle, no, it's not an important problem here. Yes, because as I said, if you increase the number of J-couplings and you have to base analysis, of course, this method works by swiping every possible value of J-coupling. So imagine that I want to swipe 20 different values for each J-coupling. This is, if there are only 3 J-couplings, that's 20 to 3 different values that I have to swipe, because I have to create a grid of all the possible combinations. If instead of 3 I have 5, it's 20 to 5, so it increases very bad. Yes.
So for you, the ideal situation would be like, okay, I know that I have 20 J-couplings, and I go one by one by increasing a lot the number of measurements in each time, or something.
I didn't understand you.
So you want to study all the J-couplings?
Yes.
For me, that if you put everything at the same time, it's very hard.
Yes.
So it would be better to go one by one.
Yeah, but if you go one by one, where do you put the other 19? I mean, you have to simulate the whole system, because if not, you will not be able to see, using Bayes' theorem at least, your signal that you receive, even though maybe the first one you match exactly with the real one, the other ones will make your signal not be equal to the one that's real. And Bayes' theorem, or
I think not when you are analyzing the data, but when you are running the experiment.
Okay. But now I get it. But imagine that you have, for example, in your molecule, 15 hydrogens and 20 carbons. So even though you want to target only the hydrogen, the J-coupling between hydrogen and carbon, when you target that with only applying pi pulses over hydrogen and carbon, you will get a lot of different J-couplings, because they do not have to be the same. Because if between this hydrogen and this carbon, maybe it's one value, but if you have a different hydrogen and carbon here, maybe it's different. So in the end, you will have a lot of 20 values to swipe anyway.
The thing, I don't know if it is clear, the thing is that you're not targeting the J-coupling. So whenever you target a nuclei, you activate all the J-couplings that this nuclei has to things. So yeah, the selectivity is not focusing a J-coupling, but you activate that nuclei, that type of nuclei. So you see all the J-couplings that are between the J-couplings and the most of this nuclei.
Okay.
So you were talking about sensitivities, right?
Yeah.
So for instance, this number in 3.3. Okay, so what's the meaning of sensitivity? Right? So, larger sensitivity implies better resolution or other things.
So, what do you mean? Larger? So, larger?
But I mean, if I give you my experiment, which is twice more sensitive than yours.
Yes. So, it means that, for example, to get the same results with the same error, you would have to, if your sensitivity is better, you would have to measure for less time, or your experiment would last less time. With better sensitivity.
So it's faster, right?
Yes. Or improve for the same amount of time, improve the error in your results.
Meaning that probably have some, we can observe hidden interaction, which are the which are inside this developed of 3/4 of noise, right?
Yeah.
And then it's true that, okay, you are always saying that at the microscale, right? So all these experiments, right? Solve the issue of sensitivity of standard NMR techniques, which is they are limited in some way to macroscopic volumes, and there are several issues Then, which is the sensitivity of some NMR experiments?
The specific value that you are asking. Actually, he told me that he had a question, a difficult question.
Evil.
Difficult question.
Let's see how do you scale.
The sensitivity of NMR. Let me think about it for a moment. Okay, so here we have more or less the sensitivities are of the order of more or less picotesla by years, something like that.
This is for micro.
Yeah, with NV centers, I mean. And with NMR, we are limited, I think, to microliter samples, maybe, or milliliter samples, millimeter sized samples.
Which are picoliters. Picoliters are millimeter size.
But this in conventional environment.
Yeah, very well.
Okay. So there's an order of 10 to the 3 in the size. I don't know if there's a direct relationship between the size and the sensitivity. Probably there is.
It's a difficult question.
Yes.
To focus because it's quite diffuse. Because you have to take my question and try to center properly. It's not easy to answer. We can.
Okay. Anything else? Okay, so thank you again.
So,